This lesson is about significant figures, which are a really important concept that is found throughout all the sciences, really, whenever you're doing calculations. So I will often shorten significant figures to sig figs. Other teachers or other places, you might see it referred to as significant digits or sig digs. I like sig figs better, so that's what I'm going to go with. So what are significant figures? So they're used to indicate the certainty in a measurement. So how certain is that measurement? How accurate is it? So when you're taking a measurement, you're usually estimating the last digit in the measurement. So if we look at an example, so you're going to measure the length of this pencil. So I would say it's about 6.86. Someone else might say 6.88 or 6.85. Right? That last digit is really an estimate because we don't know exactly what it is. Same when you're measuring something on a digital scale, getting the mass, and you'll find sometimes that last digit pops up and down. It's because it's kind of estimating that last digit. So whenever you have a measured or a calculated value, the significant figures are all those digits that are certain plus one uncertain or estimated digit. So there are a lot of rules that explain to you how to figure out which digits within a number are significant. So the first thing, anything that's not a zero is always significant. So 234 meters, there's a 2, there's a 3, there's a 4. Those are all significant, so this measurement has 3 sig figs. 95.153 seconds, again, no zeros there, they're all non-zero digits, there's 5 of them, therefore there's 5 sig figs. Okay, so that's the first rule. The rest of the rules all focus on zeros, and whether or not a zero is significant depends on where it is located within the value. So if you have zeros that are between two non-zero digits, so these are called captive zeros, they are significant. So 1004 joules, those zeros in there are significant. If you didn't have them, the number would be completely different. So there are 4 sig figs here. 12.0345 newtons. So that 0, it's stuck between a 2 and a 3. It's a captive zero, therefore it's significant. So there are 6 sig figs in that value. Okay, the next type of zero are leading zeros. So these are zeros that come before, precede the first non-zero digit. And these are not significant. So 0.02345 centimeters. So those zeros come before the first non-zero digit, the 2, so they're not significant. So there are only 4 significant figures here. And they're not significant because they're really just placeholders, right? So that you can have the values in the right places, right? That 2 needs to be in the hundredth. So those zeros have to be there to indicate that. 0.000000009 moles, which is a unit we'll get to later. Just 1 sig fig, right? All those zeros, they're not significant. They have to be there to hold the place. And then the last rule about zeros is if they follow the last non-zero digit, so these are trailing zeros, they are significant if the number contains a decimal point. So if we look at this example, 6.39000 kilopascals. So those zeros at the end are significant. So there's 6. So often if you look at a number and you think, why on earth are those zeros there? Why would they even write them? They're just zeros. Well, the reason is because they're significant. That number is accurate to that number of decimal places. So if you're wondering, like, why are those zeros there? Probably they're significant. 0.00300 grams. So here we have some leading zeros and some trailing zeros. So the zeros in front of the 3 are not significant, but the zeros after are. So this is 3 significant figures. Notice both those measurements have a decimal point, which is what makes the trailing zero significant. One more example, 4,500 Kelvin, which is a unit you may or may not have experienced before. But that's a measurement of temperature. So 4,500, so there's no decimal point here. So this only has 2 sig figs. Those zeros don't count because they have to be there because the number is 4,500. It's not 45, we can't take them away. So they have to be there. They're just holding place. So that's 2 sig figs. And the final rule is that counted or defined values have an infinite number of significant figures. They're accurate, they're completely accurate. So something like there are 24 students in the class. Well, there's not going to be 23.8 students or 24.3 students. It's just exactly 24. Or things that are defined, like there are 1,000 meters in a kilometer, and there is exactly 1,000 meters in a kilometer. So it has an infinite number of significant figures. So here are some measurements for you to try and figure out how many sig figs there are. So I recommend that you hit pause on the video, try to figure out the number of sig figs in these 8 measurements, and then once you have, you can unpause the video and check them. So here are the answers. So this 3.098 mils has 4, 0.045 grams, 2, 1.29998 micrograms, 6, 2.00 times 10 to the negative 10 meters. So this one has 3. So when you see things in scientific notation, you only look at the 2.00 part. You don't look at the times 10, the exponent part. The sig figs come from the first part. 0.003 liters, 1.009 kilometers per hour, 4, 2 million kilograms, just 1, 0.20000 millimeters, 6, right? Because there are those zeros that you're like, why are they there? Well, they're there because they're significant. Okay, so there's a few more rules because we're not just going to be looking at numbers and figuring out how many significant figures they have. We're going to be doing calculations and having to express our answers to the correct number of significant figures. So what are the rules for doing that? So when you are multiplying and dividing, the rule is that your answer should have the same number of significant figures as the number in the question with the fewest significant figures. So here's an example. We're calculating the area of a triangle, half times base of 3.2 centimeters times a height of 10.1 centimeters. So you put that in your calculator and you get an answer. But how do you round your final answer? So you look at the significant figures. So that half is a defined value, so it doesn't count. 3.2, well, that is 2 significant figures. 10.1, 3 significant figures. Which is the lowest? Well, 2. So that means your answer can only have 2. So when you put that in your calculator, you get 16.16 centimeters squared, but you can only give your answer to 2 sig figs, so you have to express it as 16 centimeters squared. And we'll go over the rounding rules at the end of the video. Now, what about if you're adding and subtracting? So the rules are different. In this case, significant figures essentially don't come into it. your answer should have the same number of decimal places as the number in the question with the fewest decimal places. So here we are, we're just adding up some measurements, 5.5 meters plus 0.597 meters plus 6.1262 meters. So you put that in your calculator and you get an answer. So how do you round it? Well, this first measurement has 1 decimal place, the next one has 3, and the final one has 4. So our answer can only have 1 because of that 5.5. So your calculator tells you 12.2232, but you can only give 1 decimal place, so your answer is 12.2. Now what about if the question has both? So if it has both, you're going to follow the order of operations. So do the brackets first, exponents, then division, multiplication, then addition, subtraction. And you kind of have to think about the significant figures at each step. So if we look at this example, 5.24 meters squared plus 3.4 meters times 0.2 meters. So BEDMAS tells us we need to multiply first. And in the multiplication, we've got 2 significant figures and 1 significant figure. And then we're going to add that to the 5.24 meters squared. So then we're going to think about decimal places. And it has 2. So we're going to do our multiplication, 0.68 meters squared. But really, that number can only have 1 significant figure because of that 0.2. So really, that's a 0.7. But we're going to keep the 0.68 just to make our answer more accurate in the end. Okay, but we have to remember that 0.7 meters squared will only have 1 decimal place. So then when we add 5.92 meters squared, we have to express our final answer to only 1 decimal place because of that 0.7 meters squared. Finally, let's just quickly review rounding. So you're doing a bunch of calculations. The first thing is to carry extra digits, at least 1 more than you need in your final answer. So carry that all through the final result and then round to the number of significant figures. If you round early, you risk the answer coming out wrong. If the first digit to be dropped is 4 or less, you drop it and all the following digits. So here's an example, 78.9432 centimeters. You need that to 3 significant figures. So you count the significant figures, so we keep the 7, the 8, and the 9. Then we look at the next digit. It's a 4 or less, so we just drop it. And we get 78.9 centimeters. If the first digit to be dropped is 5 or greater, then you increase the preceding digit by 1 and then drop the rest of the digits. So here's an example, 57.66 kilowatt hours. We want to express that to 3 significant figures. So we keep the 5 and the 7, and then the 6 is going to be our last digit. But then we look ahead at the next 6. It's greater than 5, which means we need to round up the first 6 to 7. So it's actually 57.7 kilowatt hours. When you're rounding, make sure you're only looking at that first digit. Don't round off sequentially. So it's something that some people do. So if you had 128.449 volts and you want 4 significant figures, you keep the 1, the 2, the 8, and the first 4, that's your 4, and then you just look at the next 4. Well, that's 4 and under, right? It's not 5. So you would round it to 128.4. Some people would look at that and say, okay, well, the 9 rounds up the 4 to 5, so then the 5 is going to round up that 4 to 5, which is not the case. So that answer is just 128.4 volts. So those are all the rules with significant figures, and there's a lot of them, and it'll take some getting used to, but it is a really important concept to get a handle on for all your science courses moving forward.